Okay, in this presentation, I'm going to go over statistical inference, which is basically testing hypotheses with statistics. Or, as I like to say, and as you're going to see in the slideshow, it's really about figuring out, hey, what are the odds something is going on here? The big picture. Statistics can find out whether a pattern in the data, which is what you find, you generally, you look at compare a difference of means, or you look to say, all right, women seem to favor gun control more than men. Or we find a correlation between education and support for a candidate. We have statistical measures that can find patterns in the data, a relationship in the data in different ways. And using the central limit theorem, there are various statistical techniques, which I'm not going to get too much into, but there are various techniques that allow a computer even to just look at the data and say, all right, we see that 52% of women support gun control and 47% of men support it. What are the odds that we could see this? What are the odds that we could see this difference if there was no difference? If just, sex and attitudes on gun control were both randomly distributed, right? And that's the gist of what, then they have math for all this, and it uses a central limit theorem. And the idea is, what are the odds if we had, white and black beans, white in favor of gun control, black beans in favor of it, and we had a big pot, and we just reach in and randomly pull out 2 scoops, which is what you would be doing if you were separating into men and women and it didn't matter. It would be the same as randomly pulling out 2 scoops. And what are the odds that if how we pick these 2 scoops made no difference, what are the odds we could get a 52 and 47 split? And they're probably not, if you think about it, if you had a jar that, had a bunch of beans, that might not be that weird to find. And so the whole point of the central limit theorem, and I'm trying not to get too deep into it, but kind of the idea is the central limit theorem talks, we think things are, and actually we know things are normally distributed on the bell curve when you take samples. And so whenever we are saying what are the odds that this pattern of men and women supporting gun control in this example are just random, we kind of use a thought framework that says, well, what if this was just a random sample, right? If men and women don't matter, then pulling out the men and pulling out the women would be the same as just randomly scooping out the beans. And the central limit theorem tells us, well, if you repeatedly randomly pull things out, this is what you'll get, right? Sometimes you get something weird, sometimes not, because anything random is going to be have a normal distribution. And so the statistics is very often about just saying, hey, what are the odds that this could just be randomness? And when we find that the odds are low, then we tend to think, well, no, the separation of the beans into the men and the women is in some way related, and this is something is going on, right? And what's going on? Well, that usually comes from the research design. You had some reason to think that men and women might be different, right? That gender attitudes might, in fact, affect political attitudes, that there is such a thing as gender attitudes. And you come with ideas through the research design process in with a presumption that, hey, there's something that we think there might be something going on. What statistics tests is really what it does is it tells you what are the odds that nothing is going on. That's an important point. And then as you'll see, this is where inference comes in. Let's start, before going further, right, so that's the big picture. Let's look, Whelan had at an example Whelan had. And Whelan had this example in his book of his professor calling him in, because Whelan had been taking statistics and kind of blowing it off in favor of working on his honors thesis and hadn't done so hot on the midterm. But then when he turned his attention around to it, he said, oh, this is actually kind of interesting. And he buckled down and did well on his final exam. And the professor, who is a professor, we have a sense and intuition about grades. We know that people don't. In fact, there is a high correlation between how a student does on one exam versus others. And, we don't let that hamstring us, but, we know that's naturally what goes on. And the professor saw a big change, enough to catch his eye. Now, he also, being a statistics professor, it's highly likely that this guy was doing stats on his class. I do it in some ways, sometimes, especially when I grade the curve on the discussion exercises. And so he might have calculated the mean change, and kind of looking at this, the question is, what's the change from midterm to final? So the professor might have calculated the mean change from the midterm to the final, saying that people went up. Let's say it's on a numerical scale, which would be which would be how you couldn't do statistics on letters. You can't do it. Yeah. So maybe the mean increase in grade is 5 points, and so that's the average. And the other thing that you do is you calculate the standard deviation, right, by simply telling Excel, calculate the standard deviation in Excel talk. And he might have said, all right, the mean increases 5 points. Maybe the standard deviation around that is 2 percentage points. I'm rounding these things. And you can, with the standard deviation, that tells you how the students are spread out around the mean, right? Although there's a lot more math, or actually it's really arithmetic to it. But we know from the central limit theorem, and I'm kind of skipping down to the third point, that 95, if these folks are randomly distributed, we know that 95% of the students will fall within 1.96 standard deviations of the mean, which you're free to interpret as 2 for, but it's 1.96. And so we expect if this is just, if any particular student is just randomness, right, because we know nothing, the world is like that, then we expect to see 95% within those within 2 standard deviations. And therefore, anybody farther away than 2. So in my example here, let's say it's a 5% increase we expect to see. Standard deviation's 2. So if somebody were to, let's say, in our example, Whelan goes up a whole 10 points, a whole letter grade. And the professor looks at it and says, well, the mean increase is 5%. 2 standard deviations, that's a standard deviation is 2, so 2 of those is 4. So an increase of 10, well, that's more than 2 standard deviations away. That's actually 2.5 standard deviations away. And by the way, when you calculate how many standard deviations one observation is from the mean, that's called the z-score, right? And you can, and this is actually something I calculate. I don't use it in the way I'm describing this professor using it, but when I do the discussion scores, I always calculate what's the class mean, and then what's the standard deviation on how people, the scores you get on your discussion things. And I say, okay, for everyone, they get a z-score. How many and this can be positive or negative. If you're above the mean, it's positive. If you're below the mean, it's negative. And, I use that to say, all right, here's the anchor grade, and then based on your z-score, you get more or less points away from that. That's how I curve to say, okay, I'm going to relate the grade to performance. Now that's different from what the professor's doing. He's using it to say, hey, is someone really, is this person hanging in there? Are they in fact, is the difference I'm seeing kind of normal, that we see some people do a little better than others? And in Whelan's case, if he was, I'm using these numbers hypothetically, if he's 2.5 standard deviations away from the mean, wow, he's really what we call an outlier. He's out in the tail of the normal distribution. So, at that point, the professor has to go, something's going on here. And calls in Whelan and he asks, what's going on? Now, the professor has one idea. He can speculate at this point. And one thing, based on experience, is maybe cheating. Right? Maybe the students cheated in this case. And Whelan certainly felt that he was being implicitly accused, but he never was accused because the professor genuinely doesn't know. The professor now just says, something's going on. Let me ask you. And of course, Whelan gives him an explanation. At which point that explanation, he's an honors student. He had an honors thesis. It's plausible, right? Well, he's an honors student, so I should probably look at his first grade as being below what we would have expected from him. And it's very plausible that, he went and he had something happen. So the professor had to search for the explanation of what was going on. But all of that is, to my mind, and statistically speaking, all fitting and proper. Right? And I think in the end, it's a good example of this is what statistics does. It says, hey, is this normal? Is this change something we would expect? And it wasn't, so we had to go and search for an explanation. Generally, what I'm talking about here is statistical significance, right? And in fact, would say that Whelan's grade, if it's 2.5 standard deviations away from the mean, we're now, yes, it's statistically significant. What is statistical significance? It's basically, and there's a lot of different definitions out there, but it comes down to the probability that a result, that something we've seen in the data, occurred by chance. Right? And very often we have this P, right? And they use that letter, and I usually italicize it, let you know. That's the probability. And we say that a result is statistically significant when that probability is low. Now, there's no hard and fast rule on this, but typically the number that gets used a lot is 5%, or as a decimal, it's 0.05. So when P is less than 0.05, when the probability that an empirical result, whether that be a difference in proportions, hey, 52% of women are in favor of gun control as opposed to 47% of men, or Whelan's grade, that's the thing we've observed. And different results require different tests, but all of these tests produce a p-value, right? And when that value is lower than 5%, that's the odds that this just occurred randomly, then we say, well, we probably have a 95% chance that something is going on. If there's a 5% chance nothing's going on, what you're seeing is a result of randomness, then there's a 95%, because that last little thing is, the inferences, and this is the inference. The inference is if there's a 5% chance that nothing's going on, then there's a 95% chance, based on the arithmetic thing of 1 minus p equals, if there's two possibilities going on, and the probability of one possibility is p, then the probability of the other thing is 1 minus p. And this is where we talk about 95% confidence. I mean, this is the sort of thing you hear a lot. Although when you see a poll result and they have a margin for error, that's sort of the same thing, but it's not, just a confidence interval on a polling result that we think there's a margin of error of plus or minus 2, 3, 4, 5% in a poll. That's slightly different. That's not significance. Significance goes to a result from some kind of test, either a difference of means comparison or a regression or anything that you might do. So, but this is the inference, right? And by the way, what is statistical inference? The inference comes in saying, well, we found the odds that nothing's going on, so we infer that nothing is going on if the odds are low. That's the whole inference thing. So that is what statistical significance means. And it's a very important concept, and it runs throughout statistics. Give you an example, another example. When I was in the Army, back in the day when I was in the Army and we had to polish our boots, by gummy. Because, they have boots, they don't have to polish that. I was at the U.S. Army Field Artillery Training Center. Yay. So yeah, I was a lieutenant in a training battery, which is a really terrible job to have a lieutenant. And we had this little group of folks, right? These are just this office with like 4 or 5 NCOs, and they tracked certain things, and they collected data, and for each training battery, we had batteries, not companies, because we were artillery. And as we took folks through basic training, there were several things that were tested and considered important. First was basic rifle marksmanship, BRM, and people qualified on that. And of course, you just kept the guy shooting until he qualified, and you got down to that 1 or 2 people, and you had to really work with them. But the question was, how many qualified the first time? Right, when they were being tested. So first time BRM qualifications, that was a percentage of how many of the people you had in the battery. Then we had the Army physical fitness test, and that had a score, so you could just have the APFT score. Then they had end of cycle tests, and again, everyone passed that eventually. You just worked with them until you got them through. But the other question was the first time goes. And these were the 3 numbers they used out of our 8 weeks of training, or 8 or 9, whatever it was. Very similar to a term today in Troy. And they tracked these things. And they tracked them for basically the last year. Every battery had gone through, so you had the same data for everybody. And what they would do is, after you went through your basic rifle marksmanship, these guys, on a weekly basis, every week, 2 batteries went through the same cycles of training. We had 2 running parallel. And they would report for those batteries how they did, what percentage had a first-time qualification. And then they reported the average for the training center, what everyone else had done. And here it is. The battery commander would have his boss and boss's boss, or her boss, and actually a lot of the time I worked for the ma'am, and so my captain had to answer to these guys. And if the percentage was higher than the average, there was this warm glow, this happiness. We did better than everyone else. If it was lower than everyone else, and you had to go and talk to people about it. The problem was there was no standard deviation. You had no idea. And we always had that sense. When the first words out of anyone's mouth, whenever your score was less than other folks, is you go, well, it's an average, so some people are going to be lower. Is it? And, there's a sense, this intuitive sense that it wasn't meaningful. That, the idea that, well, if we end up on the upside, we're great. If we end up on the downside, we're bad. But it's an average, so don't a lot of people end up there? There was just a sense that something was missing. And I actually had taken a statistics course, and I'm like, well, there's no freaking standard deviation. How do we know how far away our score is? We're 0.5%, or we're 1 percentage point above or below. What's the big whoop? Now, if we were above, we claimed clearly that showed our superiority. But when we were below, we were really worried about it. And so that was the problem. There was no way to assess whether the differences were significant. I did, in fact, suggest that they track z-scores, which was, weird. And Excel was not, this is the 80s, and we had computers, which we used as glorified typewriters, but, Excel was not, it was pushing it. And so this was the lead balloon, right? So, but this was a big problem. And apparently this is a big problem even in business, that, when people are being assessed on data, a lot of times there'll be a comparison to some average or some other number without a measure of dispersion, without the standard deviation, which tells you, hey, we're not measuring whether or not we're far. Is this, yes, we're above the average or we're below average, but is it significant? That is to say, are the odds that this is just randomness low? By the way, rival explanations abounded in this. The presumption was that any difference in a battery's performance was clearly the responsibility of the commander, and that's kind of a normative judgment on the Army's part. But we also felt that things like weather, the time of year, there was a feeling that in the summer when we had a large influx of National Guard folks, that they were different. And I think that, although that might have just been the bias of the folks who were active duty, but there was a feeling that there were a lot of other things our battery was really big. We had a lot more trainees than usual, a lot more soldiers than we usually have, and that spread us thin on the ground. There are all sorts of rival explanations here that never, that were used, that in the, sounded a lot like excuses, but that was another thing that came up. And it's just something to keep in mind. Okay. What is going on? Statistics can tell us that nothing's going on, but how do we know what is going on? And just a little quick point here before we go forward. In the Whelan example, it was backwards. He found out something was going on, and then the professor had to go in search of what that thing was. The Army example made kind of a institutional assumption that the command was causal. Not a terribly bad one, because the command's job is to, take into account anything that's, do you have too many people in your battery? Well, you need to figure out, reallocate resources, or I don't know what you're supposed to do, but you're supposed to overcome obstacles. And, okay. There we had an institutional presumption that the thing that's going on is the command. In the research, the process goes kind of the other way, where we start out identifying. We're interested in a phenomena, and so we identify an explanatory variable or variables. Right? You'll see in more advanced analyses, you'll have multiple independent variables to explain the dependent variable. And the research process, or the thinking that goes on at the beginning of it, lays out a theoretical reason, or it could be based on other research, but there's a big emphasis on laying out a theoretical reason for thinking those explanatory variables are what is going on, right? And that's where we generate our hypothesis and all that other stuff, which I'm going to get into. But the whole point is the idea of you have a reason to think something is going on. And we're going to look for a correlation between the independent variable and the dependent variable. If we think gender makes a difference in gun control, we're going to separate out respondents by gender and look at how they respond. Right? And then what we're going to ask, statistics is going to tell us, did that make any difference, or is it still just randomness? Does it still look like nothing is going on? And the important thing to keep in mind is you have a reason. If you're doing research, you have a reason for thinking these explanatory variables are important, and thus those translate when you operationalize them into indicators and state a research hypothesis. We now move into the realm of having something, an empirical result, and we expect something to be going on. And we know ahead of time what we think is going to be going on, so that when statistics tells us what are the odds that nothing's going on, our explanation for what the filling in the blank of something has already been accomplished. Okay, hypotheses. You have the research hypothesis, often referred to as the alternative hypothesis. And that name, alternative, only makes sense when you have this whole process of statistical inference in your head. Okay, so we're going to put a pin in that for a couple seconds. But the research or alternative hypothesis is the posited relationship between the independent and dependent variable. In other words, it identifies the something that we think is going on in the situation. Now we have the null, then the second one is the null hypothesis. This says nothing is going on. Right? There is no relationship between the variables. So when you go out and you have this independent variable and this dependent variable, and you go and you search for some statistical relationship, again, you run a regression, you do a correlation, you just look at the difference of means between two when you sort the groups out by the independent variable. The null hypothesis says there's nothing going on. Anything you see is simply the result of randomness. In the we have a certain amount of variation in the data, and you're just seeing randoms. And it's kind of like you're seeing Mickey Mouse in a cloud. Right? Mickey Mouse really isn't in the cloud. You're just seeing a pattern in a randomly occurring event. Now, the importance here is going to be that if you reject the null hypothesis, well, what could it be? Well, we have the alternative. If something's going on, what's the alternative of the null? Right? That's why they call the first one alternative. It's a terrible name, actually, in terms of if you're not in thinking about this process of statistical inference. The key thing, though, is that statistics only test the null hypothesis. Right? That's what they can do. That's what the math can do for you, is they can say, what are the odds that nothing's going on? And this is one of the little secrets, is statistics can't prove there's a relationship. It can just test a null hypothesis. You don't see, and this is the point, you don't actually test your hypothesis. You test the null hypothesis. And then when you reject it, you're left with, your hypothesis, last man standing, basically. That's one term I like to use here. And that's all it is. All right, I've kind of already gone through this, but a little repetition here. In hypothesis testing, the researcher has a reason to think there's a relationship. Right? So that is theory and past research. Okay, that's again very important. It's not part of what you're doing when you're actually testing stuff. It's part of the research process. It's something you've already done before you got there. Okay, and therefore it's not necessarily taught in statistics books in the section with hypothesis testing, but it's in the whole book, I guarantee you. Statistical methods. Now, you're going to go through and you're going to, in some way, you're going to find a relationship, right? Or you're going to see if there is a relationship. And I have this here because you may not find there's a relationship. We could have separated out men and women's attitudes on gun control and found out that 52% of women are in favor of gun control, and guess what? 52% of men are. There'd be no relationship there. They came out the same. There was no variation. However, more often than not, we will find, because 52 and 52 lining up seems weird. Very often, you will find you'll find some relationship. And the question with a relationship is always, what direction is it in? Direction is in my example, more women favor gun control than men. Right? So we're looking for a direction of relationship. And then there's a strength. Again, in my example, 5% more women favored gun control than men. The strength of the relationship is being female makes you more likely to support gun control. How much more? 5%. Or it's 5% more likely that you'll favor it. Right? That's the strength of the relationship. And by the way, this holds for everything, direction and strength. Significance testing establishes the odds, or P, that the null hypothesis is true. That, hey, there's nothing going on. If we reject the null hypothesis, then the alternative hypothesis is all we have left. And therefore, it may be true. At this point, you should see how tenuous that support is. It's support. You have subjected your hypothesis to a test. What are the odds that this is all just BS, just randomness? And it survived. But we haven't directly observed the thing. We haven't, we basically said the null hypothesis. We rejected, the technical term is we can reject the null hypothesis. Therefore, we have some confidence in our alternative or our research hypothesis. This is one reason why social science results are often they're expressed in cautious terms. Maybe, we say this supports the hypothesis, right? Without proving it. We don't actually prove it. That's all it is. And by the way, that's what we do that's what folks do in statistics. I won't even say we. I don't do it that much, but we find a relationship, direction, and strength, and then we find a p-value, significance. And in my example of 5247, I don't know. That's 5247. That could be the result. I picked those numbers because that's when you need the significance. Because significance, a lot of times, small differences will nevertheless be significant. And sometimes big differences might be not significant, right? We don't say insignificant, by the way. We say not significant. That's something why you have to have the testing and you have to run the numbers. Okay, so to sum everything up, like I just did, statistics tells us the direction of a relationship between independent variable and dependent variable. It tells us the strength. It also tells us the odds the observed relationship occurs by chance. Notice I led with the names before and finished with the name after. I just always want you to keep in mind that idea that this is all we're doing. And whatever technique you're using, again, it could be a simple difference of means test, or it could be a multivariate regression. All statistics will do these things. We'll get a direction, usually a plus or minus sign, and we'll get a strength. As you'll see when we get around to talking about regressions, it'll be a coefficient. How much does the dependent variable change when the independent variable changes by 1? And that will all, sometimes the direction and strength will be in one number. If I have a plus 0.5, that means that for every in a regression as a coefficient, we'll get to it later, but that number is going to tell me, okay, the sign is positive, so the direction is positive, and what's the strength for every increase of 1 in the independent variable? The dependent variable goes up by 1/2. So sometimes one number can tell you both. That's what I'm saying. And then we have significance, and that's the p-value. Sometimes, by the way, when you get into regression, significant results often have an asterisk by them. Right? A lot of times they don't necessarily report the p-value. They will just put an asterisk by a empirical result, like I say, a coefficient that's significant. And I often describe reading statistical results as the asterisk hunt. You go in, what was significant? And then, all right, Well, first you read the whole setup to find out what the variables are, and then you go and look at the table and you look where are the asterisks, because those are the things they found that are significant. And so a 0.05 with an asterisk by it, one number with an asterisk tells me all of these things when reading this. But these are the three things we're looking for. The story that supports the alternative hypothesis is so very important, and I really am hammering down on this, that statistics is only really effective when it is conducted in a research process where we have gone through the literature, where we've gone through the theory, and we have an explanation that we think holds water. The explanatory variable, the theory tells us this model of the world. Here's what we think is going on. And then we derive from that some testable hypothesis. And then statistics tells us, first we find out if there's the predicted relationship. Because sometimes you may predict a positive relationship and find that a negative one occurs, at which point your prediction's out the window before you've done any significance testing, right? When something's not in the predicted direction, that's a negative. That it might be interesting, but it's a negative. You've kind of blown the hypothesis out of the water. That can happen and does happen, actually. But then, we say, what are the odds that nothing was going on? And because the support for the alternative hypothesis is simply that the opposite isn't true, you have to have a belief that, that is the explanation, right? If something's going on, it must be what I have hypothesized, what my theory tells us is going on. But this is also why the testing of rival hypotheses is so important. Because, again, statistics just tells us that nothing is not going on. It's a double negative, right? And so what's the positive? What's the positive explanation here? And getting a double negative result is not the same as getting a positive one. And getting, being told, when you reject the null hypothesis, the alternative, if there are multiple alternative hypotheses, well, you got a problem. And that's why finding tests that will, you'll test both of them, and then you find that your rival hypothesis doesn't hold any, or, you can't reject the null hypothesis there, but we can reject it when we're looking at mine. That's why it's so important in this sense. So, hope that explains kind of the basics. I'm trying to give you this intuition because it's you have several explanations. You have Whelan has really explained this well. Pollack, he kind of leaves it later till Pollack. A lot of times, statistics they only explain the significance testing in the context of running whatever particular statistical operation they're teaching you. And each statistical operation has its own tests of significance, and we get lost in the weeds. What I wanted to give you was this idea, because this is so important, not just for doing this kind of research, but also for reading it, for understanding, hey, what am I looking for? I'm looking for direction, strength, and significance. Let me go search for asterisks, or what, depending on what the person's doing in that paper. And also, I think this should emphasize how important those first things are. That's why you do a research design in this class, because that first stuff is not, that discussing of all explanations for the dependent variable is not just fluff. It is very important. In some ways, maybe even more important than actually doing the statistics, because Excel can do that for you.